Many people, when first encountering EmbedClaw, mistakenly assume that, as long as you connect a model and say turn on the light, it will be able to directly control the GPIO. But the reality is, a large language model cannot directly manipulate hardware. It can only interact with hardware through tools. Because a large language model is essentially just a program that performs input comprehension plus reasoning plus text generation. It is responsible for decision-making, but it does not possess the ability to execute hardware operations. Real hardware control must be encapsulated by you into a tool and then called by the model. This is exactly the core philosophy of EmbedClaw. Clearly separate LLM, agent, tool, and channel. The model is responsible for understanding and invoking, while the code is responsible for execution. Many people also confuse skill with tool. Skill is the strategy. Tool is the execution interface. In one sentence, skill decides what to do. Tool is responsible for how it is done. Next, let's take the already working GPIO control example from the project to walk through how to add your own tool in EmbedClaw for the AI to invoke. Step 1. Give the tool a name that the model can understand. This name is meant for the LLM, not for the compiler. When the model makes a call later, this is the name it will use. Naming suggestions. Use English. Keep the semantics clear. One name should express exactly one capability. Examples. Step 2. Write a good description. Tell the model when to use me. This part is critical. It essentially serves as the instruction manual for the model. Using GPIO control as an example, two things need to be done. 1. Define the capability scope. Control ESP32 GPIO. Supports on offset toggle get. 2. Emphasize the invocation constraints. All GPIO operations must go through this tool. The model must not fabricate results. This is the core of tool design. Step 3. Use input schemation to constrain how the model passes parameters. The key to making a tool reliable is not just knowing that it should be called, but ensuring it is called according to the rules. Take the parameters of GPIO control as an example. The parameter must be an object. Pin, integer, action, on-offset toggle get, level, only needed when action is set, and must be exactly 0 or 1. This step essentially defines a function signature for the model. It is not a suggestion, it is an enforced rule. Step 4. Write the actual execution logic inside execute. Everything before was about how to call. This step is where the real execution happens. Core flow. Parse the JSON parameters. Validate legality. Execute the action. Write the result to output. Note, the tool returns a string result, not a code return value. Step 5. Register the tool into the system. Simply writing a tool is not enough, it also needs to be registered. Here, tool registration is performed by defining a dedicated registration function. The registration function will be automatically invoked through macro expansion. Finally, register the tool into the tool registry so that it can be invoked by the model. Final summary. The model is responsible for invocation, the tool is responsible for execution, you are responsible for defining the rules. Once you have mastered this workflow, you can easily extend it to relay control, servo control, sensor reading, buzz, various local interface calls. The key is not how powerful the model is, it's whether you have clearly defined the boundaries of capability. The more powerful the model, the more it needs well-designed tools. Once you understand this, you can use the same approach to build any AI plus hardware system. The code is open source. For more information, please visit the GitHub repository. Wireless tag, dedicated to ESP32 development boards.